Good morning, everybody. This is lecture 26-2, or I guess 1 in this case, based on superalloys, nickel-based superalloys. So the title of my study was Additive Manufacturing of Nickel-Based Superalloy Inconel 718 by Selective Electron Beam Melting, or SEBM. It was published in the Journal of Materials Research, and the scope of the study was to study the relationship between processing parameters and microstructure. And one of the key questions they asked was, what effect does changing the spot size of the beam have on the grain structure? So experimental approach, they used gas atomized nickel-based superalloy. There's a picture of gas atomized powder. The process conditions that they changed throughout the study was deflection speed, or just how fast the beam is moving along, the beam energy, and the beam spot size. They left all the other process conditions constant. So like the hatching pattern, they did one layer this way, and then they rotated 90 degrees. And then they kept the line offset and the layer thickness and preheat temperature the same. And for this study, they just made one run and made 9 cube-shaped samples from it using SEBM. So the key results from the first study, so how do the process conditions affect density and top surface unevenness? So the left graph is for the larger spot size, I think, 500 micrometers, so the defocused beam, and the right graph is the focused beam, and in both cases, the black markers are like preferable conditions, so each one of those markers is a different process parameter condition, and the black dots is what was preferable, and if it was white, then it was porous, and if it was gray, then it was dense, but it was also uneven. And we'll get into why that happened. But that was the same in both cases, except this one is just the slope is changed on the right. So they theorized that the porosity occurs due to the beam moving too fast or too high deflection speed, or low beam energy, which kind of makes sense if you don't get the sufficient melting from either moving way too fast or not having enough energy into the material. And then unevenness occurred from too much energy, so slow deflection speed or too much beam energy into the material. And I was trying to think of an example, and if anyone's ever like stick welded or anything, if you're going too slow, then you get like too much of a puddle, and then it's just gonna like splatter and kind of go everywhere. So that might make a little more sense. Key result from study 2 is, what does the beam spot size have on the grain structure? The defocused beam resulted in a better columnar grain structure, which was preferable for high temperature applications. So that's on the left, the defocused. And the right was the focused beam, and you can see all these kind of stray grain formations, and they also had a lower mean grain width. So that's this graph over here. So the black dots were the focused beam, and the white were the defocused, and on the left is the grain width. So you can see that with the focused beam, all of the grain widths were smaller than the defocused beam. And in summary, porosity is a result of insufficient melting, and surface unevenness is a result of high forces exerted on the melt pool. In this study, the defocused beam spot size, or the larger spot size, was preferred for 2 reasons. First is at a higher peak energy, the focus spot size had a higher peak energy density which led to higher evaporation pressure or vaporation pressure and more melt motion, which led to more surface unevenness. And the second reason was that the focus beam enhanced the formation of new grains, which hindered the development of the columnar structure that they wanted. See, for my own summary, I think that the paper was relatively straightforward and easy to follow, although, to be honest, I didn't really understand a lot of the grain literature that they were talking about. But other than that, it was pretty good.
Hi, good morning. I'm Nick Corright. My presentation was on superalloys, specifically Inconel 625, which is a nickel-based superalloy. It's been used in the aerospace industry since the 1960s. It's known for its perfect combination of tensile, yield, and creep strengths, as well as being corrosion resistant. This is the powder used in the experiment. It has an average particle size of 35 micrometers. It's spherical in shape and has a smooth texture. So my paper was Microstructure Characteristics of Inconel 625 Superalloy manufactured by Selective Laser Melting. It was from the Journal of Materials Science and Technology in 2015, so it's a pretty recent study. The scope of the study was the microstructure of SLM Inconel 625 parts. So previously, Inconel 625 has been studied quite a bit, and most of the studies focused on the macrostructure. And the one study I mentioned that talked about the microstructure was using a different process. So these guys wanted to experiment with looking at the microstructure from the SLM Inconel 625 parts. So the key question they asked was, what is the effect of heat treatment on the microstructure of the Inconel 625 parts? This picture here is a inverse pole figure from the samples, and it shows the texture of the samples, and each color represents one grain. So the material used for the experiment was the Inconel 625 alloy, and that's the composition of the alloy right there. It's 53.5 weight percent of nickel, has chromium, iron, and it talked about the alloys that actually, or the elements that strengthen the alloy were the Nb, which is niobium, and Mo, which is molybdenum. So the process conditions examined were the lattice constant, the distribution of carbides, and the microhardness. And they used a scanning electron microscope, electron backscattering diffraction, and X-ray diffraction. So this picture here is an optical metallographic image of the sample after it had been annealed at 1150 degrees Celsius. So the first result from the study is what is the effect of annealing temperature on the lattice constant? So the lattice constant is actually the physical dimension of the cell unit and the lattice structure. So the graph on the left is the X-ray diffraction results of the different annealing temperatures. So they annealed the parts at 700, 1000, and 1150 degrees Celsius. So the graph on the left, it was just showing that after the annealing, the microstructures of the samples were still basically the same as straight out of the selective laser melting process. And the results were that the lattice constant decreases slightly with the annealing temperature, and this is due to the precipitation of carbides during the phase changes due to the annealing temperatures. So the second result is what is the effect of heat treatment on grain orientation? And after they annealed at certain temperatures, the grains kind of melted into this rectangular shapes, and they all had the same orientation, showing that the grains had a preferred orientation after the heat treatment. And these two pictures represent this zigzag grain boundary, and they talked about how this is generated by the MC carbides during the process, and how the zigzag pattern helped improve ductility and toughness and the overall performance of the alloy. So the key conclusions from the research paper, the microstructures after the heat treatment are similar to the SLM original state. However, the lattice constant decreases slightly. The grains have preferred orientation, and the zigzag grain boundary forms after the heat treatment. and the hardness of the SLM parts was very high due to the fine microstructure of the parts. My personal critique of the research, I guess the information on the heat treatment of the SLM Inconel 625 parts would be useful. I found the paper very difficult to follow. I really just couldn't understand what they were trying to convey and what they did. Actually, I never even, I don't think they explained what their sampler specimens looked like. So there's a lot of unclear things in there. I just kind of had to follow along and figure it out.
My name's Deacon. I also read a paper on Inconel 625. However, the paper I read used a different manufacturing technique versus the centered laser melting. This one in particular uses electron beam melting. So the title of the paper was Properties of Inconel 625 Mesh Structures Grown by Electron Beam Additive Manufacturing. It too was a fairly recent study done in 2014. The paper was in Materials Science and Engineering. The scope focused on the relationship of the electron beam parameters and how they affected physical properties of the mesh structure, such as mass, relative density. The key question observed was how do beam current, speed, and focus affect mesh properties when producing fine mesh structures. So the material used was rotary atomized powder with a composition of the Inconel alloy 625 with a similar composition that Nick showed in his presentation previously. Again, the conditions examined were specifically beam current, speed, focus, as well as mesh cube mass and relative density. And the characterization tools used was a commercial Arkham A2 electron beam melting machine. So the first result from the study, how did beam current and speed and current affect the mass and relative density? As you see with the one on the left here, with the beam fully focused, which means it was not offset to any degree, the mass of the cube will decrease with an increase in speed. So this is on the x-axis here, we have the beam speed in millimeters per second. The mesh cube mass is on the y-axis here, and this was for beam currents of 2, 3, 4, and 5 milliamps. And on the flip side of that, for a fixed speed, you can see as the current increases, the mass of the cube will increase. On the right, the same parameters were compared with a ratio of the beam current over the beam speed, and again with an increase in, it may be a little more difficult to see, but with an increase in beam current, there will be generally a linear relationship of increase in beam mass and relative density. The second key result from the study throws in focusing the electron beam. So when you account for different offsets in the focus of the electron beam, for a fixed beam energy ratio, which is the ratio of the beam current over the beam speed, the mass will increase for an increasing beam offset. So here again you have your lowest beam offset, which was 0, which was the same results that we saw on the graphs before with no offset. And then as you increase the offset, both the mesh cube mass and the relative density will increase. And the relative density was basically the density of the original mesh cubes that were made, which had dimensions of 30 millimeters by 30 millimeters by 30 millimeters. And the original density, I think, was something like 0.08, I believe. So the key conclusions from the research paper was the mass of powder melted is roughly proportional to the energy delivered to the system when producing the part, and that the defocused beams, as shown in the previous graph here, the defocused beam distributes energy over more of the powder bed, and this creates a more even melting of virgin powder during the process. My personal critique of the paper was that it was a very well-written paper with well-documented results. It was easy to follow and understand the conclusions that they reached. However, there was a lot of information in there, a lot more that could be contained within a short presentation such as this. They also went and observed factors such as stress and strain on the structures once they loaded after they were produced, and this kind of research was useful for applications involving the need for parts to have varying physical properties or distribution throughout the same part. The paper specifically mentioned an osteo application with bones and how different interfaces between bone tissue could experience different mechanical properties and physical properties, and how something that would have a varying distribution of mechanical and physical properties would be useful for such an application.